All right, so yesterday we finished up talking about chemical versus physical changes. Today we're going to talk more about measuring things, so measuring their physical properties. And scientists have kind of their own special way of measuring just about everything. And we try to be uniform across the entire globe. And so we use a system called SI. So scientists use SI units. And what SI stands for is this French term, Système International basically meaning it's a systematic system that's used across the globe, right? So let's come up with a list of physical properties. And we said you can measure length. You're not changing the type of matter when you measure length. You can measure mass. Those are two common ones. You can measure volume. We did that in lab. You can measure temperature. You can measure time. You can measure current, as in electrical current. You can measure luminous intensity. That basically is how bright something is. So maybe you've got a really bright light bulb or a really bright TV. And you can measure amount. Basically our system for counting. All right, and then we've got special SI units. And then we've got an SI symbol. All right, so the SI unit for length, what do you guys think it is? If you go into Europe, or even Canada for that matter, how do they measure length or distance? Meters, right? So meters are the SI unit. Oh, let me clean this up. My handwriting's getting worse. And the SI symbol for meters is going to be lowercase m, not capital M. So always make sure you double check whether or not you're capitalizing something. All right, what about mass? How do we measure mass again? You did this in lab? Grams. Sometimes people will use kilograms, and I'll talk about the difference here in a second. And you can do kilograms by adding a little k in front of the g, right? So lowercase k. And I'm going to put an asterisk here because oftentimes you'll see grams used in chemistry, but kilograms used in physics. All right, what about volume? How did we measure volume? Milliliters, right? So when you put pennies in that graduated cylinder, you were measuring changes in milliliters, right? Usually, most people use liters. And for liters, you want to have a capital L, not a lowercase l. All right? Again, I'm going to put an asterisk there because chemists do things a little bit differently. We prefer to use milliliters for the most part. All right, temperature. What's the SI unit for temperature? So if you go to Canada or Europe, anywhere else? Celsius. However, chemists are even more persnickety than that. We use a system called Kelvin. That's named after the scientists that investigated that. And Kelvin's a little bit interesting. We're going to talk more about that later, but the unit for Kelvin is capital K. And again, chemists quite often use Celsius, so I'm going to put an asterisk and come up with our alternate chemistry ones. All right, what about time? How do we measure time? Seconds. It's pretty easy. And the symbol for seconds is just lowercase s. Current is a little bit different. We're not going to get into electricity very much, but if you go on and take physics, you will. And you can measure currents in amps. And the symbol for amps is a capital A. Luminous intensity, same thing. We're not really going to get into it, but it's referred to as a candela. And that's abbreviated CD. And then the last one is really important, just simply counting things in chemistry. Does anybody know what we use for chemical counting? We use the mole, not the rodent, the system of counting. And for mole, we abbreviate that MOL. We're going to spend a lot of time this term using moles and converting to and from moles, but it's a pretty simple process. Let's go down here, and then we'll say chemists will often use grams, milliliters, and Celsius. So we do kind of break the rules a little bit with the SI units. Does that make sense? All right. So moving on, chemists oftentimes have to measure things that are incredibly large or incredibly small. Often measure large or small things. And that has to do with the nature of science, right? Most of what we're measuring in our day-to-day life is manageable, but when you're talking about things in the universe, you're dealing with incredibly large scales. So if you're an astronomer, you're thinking about things as large as the sun. If you're a chemist, you're thinking about things as small as an atom. All right, so let's take an example of this, and I'll show you my favorite experiment for a large measurement, and that is the experiment that was done to determine the mass of the Earth. And this experiment is called the Cavendish experiment. I've got the link on OneNote, but if you are curious about it, you can read about it here. It was pretty crazy that they were able to determine the mass of Earth in about 1798, and they were able to do that to a certain degree of accuracy. They were pretty dang close all the way back in 1800. So it was a clever experiment. And what they determined was that the mass of the Earth is incredibly big, as you can imagine. It's 5970, and then let me count. This many grams. It's tough to put on a scale, right? So if you look at the number of zeros here, we've got a huge number of zeros. Most chemists don't like writing that many zeros simply because it's uncomfortable, it takes too much time, takes too much room. So what they do is they say, all right, this final digit where the decimal point goes, let's move that. So what I'm going to do is I'm going to move that decimal point at the end of the number all the way up to after the first digit, right? So I'm going to move it after the 5. So now the question is, well, how many places did we move the decimal? What do you guys think? Yep. I would say we moved it 27 spots to the left, right? So what chemists will do is instead of writing this giant number, they'll say, all right, it's 5.97 times 10 to the 27th grams. And basically this just means we moved that decimal point 27 units over from where it was initially as a whole number, right? And this is called scientific notation. Oh. So it is a little bit weird to think of constantly moving these decimal points over, but obviously this is a lot more manageable to write out than all of the zeros. Let's do another example at the opposite extreme. And we'll do the mass of a hydrogen atom. And you can imagine a hydrogen atom is going to be incredibly small. Again, we're going to have a lot of zeros. Let me do some counting here. Two, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 zeros, followed by a 1, 6, 7. So that's the mass of one hydrogen atom. In this case, our decimal point is on the left-hand side, right? So what do you think we should do? Probably move it to the right. So like I said, you always like to have your decimal after your first whole number. So I'm going to move it after the 1. Let me actually show this more clearly. So we're going to move it right after that 1. So it will be 1.67 times 10 to the what? How many places did we move that? We had 23 zeros, but we're actually moving it one more past the 1, right? So in this case, it'd be 10 to the 24th. Or am I missing something? It should be negative, right? We're going to the right-hand side, so it should be a really, really small number. Make sure you remember to include that negative value if you're going to the right. It's only positive if you're going the opposite direction. All right, so this would be 1.67 times 10 to the negative 24th grams. And this would be proper scientific notation for the mass of a hydrogen atom. Does that make sense? It's commonly used all over science and even in your day-to-day life, depending on how much science you do in your day-to-day life, I guess. So let's take a look at some prefixes that can be used in addition to scientific notation. So they can be used instead or in addition to scientific notation. So let's take a look at some examples. And I'm going to take Batman as my first example. So Batman, the Christian Bale version, has a mass of 95,000 grams. It's a pretty heavy guy. All right, so if we think about Batman, let's first do scientific notation. And I'll do that over here. And if we do scientific notation, how would we represent his mass? We want to try to get rid of all the zeros. Well, just like we did before, let's do it the way we just saw. We've got that decimal point. Sometimes it's not even shown, but it's assumed to be there. And we're going to move this over here right after the 9. So it'd be 9.5 times what? Times 10 to the 4th, right? So you can say 9.5 times 10 to the 4th grams. Or you can do this with prefixes. Does anybody know the prefix that is commonly used for mass? Looking back up in your notes. Kilograms, right? Does anybody know what a kilo of something is? 1,000, right? So typically when you're getting your mass in the hospital, they'll give it to you in kilograms, and they'll say, this is 95 kilograms. And this K basically means 1,000 grams, right? So another way of thinking about this is if you take 95 times 1,000, you get 95,000. Right, so you can plug in that prefix and still get to that same answer. It's just a different way of expressing that number. Does that make sense? All right. There are a lot of prefixes we have to remember as scientists, so I've given you a handout of the most important ones. This isn't an exhaustive list, it's just my favorite ones. And the first one that's really important is nano. So I'm sure a lot of you have heard about nanotechnology, right? Nano is something very, very, very small. Specifically, it's 10 to the negative 9, meaning 1 billionth of something. So it's an incredibly small number. Micro, with that symbol, it looks like a U with a tail, is 1 millionth, or 10 to the negative 6. Milli is M, lowercase m, and it's 10 to the negative 3, and that's 1/1000th. And then centi is 1/100th, or 10 to the negative 2. The way I remember all of these is these first four are smaller, right? They're smaller than their original unit. And then down here, we've got kilo. Kilo is 1,000 times, so now it's bigger, it's not smaller. And kilo, like we said, is 10 to the third or 1,000 of something. So these are really important units that I do want you to memorize. What some students do is just keep flashcards next to their bed. So get note cards and then just every night before bed flip through them. If you do that for a week or so, you've got them down pat. You won't forget them after a week. Down here, it's got a system of conversions. We're going to practice this a lot more later, so don't worry about these too much right now. We're going to spend probably a couple days doing unit conversions. In addition to that, at the end here, we've got table 3. This is a list of English relationships to things. Like I said, in the US, we use this backwards system where we have things like inches and miles instead of centimeters and kilometers, and this gives you the conversion that you need to convert between the two. And again, we'll practice unit conversions later on. There is one that I wanted to point out. It's a little bit odd. And this is an angstrom. So 1 angstrom is 10 to the negative 10th meters. And this is a unit that's used almost exclusively in chemistry because the distance that atoms are from one another is usually about a few angstroms. So it's just a convenient unit for chemists to use. Sometimes they use nanometers though, because if we look at angstroms, it's 10 to the negative 10. A nanometer is 10 to the negative 9. So they're pretty similar to one another. Does that make sense? Okay. I did want to show you guys something though, and this is pretty important, is let's do nano meters first. So 10 to the 9th nanometers is equal to 1 meter, right? So you have a lot of nanometers that can make up 1 meter. The way I remember this is the bigger number goes with the smaller unit. Right? We said that nano is smaller than the base unit, so it should have the bigger number. We don't want a negative 9 there. We actually want 10 to the 9th, and that confuses students sometimes. But what you can do is convert this into 2 different relationships. What I tell people is you can do 1 meter over 10 to the 9th nanometers, or you can say 10 to the 9th nanometers over 1 meter. Why can you do this either way? Does anybody know? They're the same number, right? If you divide 1 divided by 1, it's going to be 1, right? So it doesn't really matter if you have it right side up or upside down. You can use it either way. It still is going to be equal to 1. Alternatively, you can do this with micrometers. All right, with the micrometer, it's going to be 10 to the something I'll have you guys help me out with this. Equals 1 meter. What should the unit be for that question mark? Or what number should it be? 6, right? We know it shouldn't be -6 because it's the smaller unit. And so again, just like before, we can say 10 to the 6 micrometers over 1 meter. Or alternatively, you can say 1 meter over 10 to the 6 micrometers. Either one is acceptable. Does that make sense so far? You guys want to see the rest of them, or do you kind of get the trend at this point? Show of hands if you want to see the remaining ones. No? All right, that's good. That means you're getting it, hopefully. All right, so let's do some practice. And I've got some practice problems for you that are actually similar to your problem of the day. So the first one is replace the base 10 units with a prefix. All right, so for the first one, I've got 8.01 times 10 to the -6 grams. For the next one, I've got 1.05 times 10 to the -3 meters. For the last one, I've got 7.9 times 10 to the -3 liters. So I'll give you guys a minute to think about this, and then check with your neighbor to see if you're doing the same sort of process. Let's try the first one as a group. All right, we've got 10 to the -6, and we want to replace that with a prefix unit. What is 10 to the -6? Micro, right? And that's that U with the tail. Looks like that. So we could go ahead and we could say this is 8.01 micrograms, right? Nice and easy. All right, next one, we've got 10 to the -3. What is that? Milli. So we've got lowercase m, not capital M. Sometimes students use capital M. That actually means mega, which is 10 to the 6th, not 10 to the -3. All right, so this one would be 1.05 millimeters. All right, and then the last one is pretty similar. We've got 10 to the -3, which again is milli. So we would say 7.9 milliliters. So lowercase m, capital L. It's important to remember to keep it lowercase. Make sense? All right, let's do the opposite one. So this time we're going to replace the prefix with the power of 10. All right, so I'll give you a few examples. First one, we've got 45 milligrams. Next one, I've got 125 nanoseconds. And then next one, I've got 10.7 microliters. We want to get rid of the prefix and go back in the opposite direction. In fact, I'm going to make these smaller. Let's do the first one as practice, and I'll show you one nitpicky thing that scientists worry about because we have nothing better to worry about. All right, what does the lowercase m mean? Milli, and that is 10 to the what? 10 to the -3, right? So we would say, all right, this is the same thing as saying 45 times 10 to the -3 grams. However, we typically only want one digit and then a decimal followed by other digits. So we need to change this a little bit more. What I mean by that is we've got this imaginary decimal point. What we want to do is we want to move it right after that first digit. All right, so if we do that and we shift it one more to the left, what will happen? Yeah, so will this be 4.5 times 10 to the negative 2? Or will it be 4.5 times 10 to the negative 4? What do you guys think? It's tricky, right? If you go left and you're moving your decimal point left, your 10th place is getting more positive. We saw that in the Earth example. And if you're going to the right, it's getting more negative. So in this case, we're going to the left. So we want to go in the positive direction on a number line, which means that this must be 4.5 times 10 to the negative 2, right? Because that's getting more closer to the positive side. So most chemists would prefer to write it this way. You're not wrong if you write it in the 45 times 10 to the negative third method either, but most people will write it that way. Does that make sense? I'm normally not super picky, but I do want you to know how to go back and forth. So make sure you are comfortable moving decimal points and knowing whether or not the 10th place goes more positive or more negative, if that makes sense. All right, so what do you guys think for the next one? What does the nano unit stand for? 10 to the negative 9. All right, so then we'd say, all right, this is the same thing as 125 times 10 to the negative 9 seconds. What will that be if we move this decimal point right after the 1? Okay, it's going to be 1.25 times 10 to the something. I want you to check with your neighbor and see if you agree. If you don't agree, try to explain it to your neighbor. All right, we moved it 2 spots. That means our options are 10 to the negative 7th or 10 to the negative 12th. Raise your hand if you picked the negative 7. Awesome, we're on the right track. So 10 to the negative 7, we're moving it to the right, so it should be getting closer towards our positive direction. So 10 to the negative 7 seconds. The other thing I'm a huge stickler on is numbers without units are meaningless, right? So always include your final unit of seconds. Otherwise, I have no idea what you're talking about. You could be counting cats for all I know. All right, last one. We've got micro. What does that stand for? Micro. The 10th place, though, what is that? 10 to the negative 6. All right, so we know that this would be 10.7 times 10 to the negative 6 liters. Just like before, we're going to take this decimal point. Let me keep it consistent. Move it right after our first whole number, which in this case is 1. So we're moving it 1 spot. What will our final answer be? It's going to be 1.07 times 10 to the what? Negative 5, exactly. There you go. So not too bad, but it does take a little practice to get used to. All right. I'm a big fan of estimating things. And in order to estimate units, I like to have some sort of benchmark value. So 1 liter is about the volume of an Nalgene. Does anybody have a Nalgene in here by chance? I don't think so. Oh, right there. So do you want to hold that up high? It's that standard backpacking water bottle that you see all around. That's 1 liter. So that's a really useful trick for estimating. Using that, how much do you think is in a milk jug, roughly in liters? How many Nalgenes do you think you could use to fill up a milk jug? Probably about 3 or 4. So you can use that as a rough guide for estimating. It's really important to develop that skill of estimating. If you said, oh, I can fit 1,000 Nalgene bottles into a gallon jug, you'd be way off. So it's good to have a ballpark estimate. You don't have to be accurate to a high degree, though. It's just a good tool to have. All right, 1 meter. What's a common thing in your day-to-day life that's about 1 meter? Anybody know? A yardstick? Yeah, a yardstick is about 1 meter. Another useful trick is if you hold your finger out away from your body, it's about the length away from your finger. So that's an approximation. In fact, I don't know if this is true or not, but I think that's how they actually developed the yard. There was some king, and that was a measurement to his finger. So it's, again, not going to be an exact amount, but it's a good estimating tool. All right, 1 kilogram. This is another Nalgene reference. So that blue water bottle that you were holding up, if you fill that with water, that weighs about 1 kilogram. It's about 2.2 pounds. All right, and then 1 gram is about the mass of a paper clip, assuming it's a, small paper clip. So for example, if you said, oh, this table weighs 1 gram, you'd be way off. You'd want to estimate a little bit more accurately than that. So estimating tools are pretty useful. Does that make sense? All right, now what we're going to do is practice measuring things in a lab setting. Sometimes it's not super easy, and that's where our next handout comes in. And there's a few rules when you're measuring in the lab. Most measuring tools have hash marks on them, right? So if you're using a tape measure, that has hash marks. If you're measuring volume in a graduated cylinder, you saw hash marks on those graduated cylinders, right? When you're looking at those hash marks, the first thing I do is look at the units that those hash marks represent, and then I estimate 1 digit further. And we'll do a few examples. So let's take a look at the first example. What do the hash marks represent? Are they the ones place, tens place? Yeah, it looks like the ones place, right? Every hash mark goes up 1 ones place unit, if that makes sense. All right, that means we need to estimate out to the 10th place, right? So how would we measure the first one? For this example. We know it's in between 15 and 16 for sure, right? That's certain. Absolutely, it's between 15 and 16, so it should be 15 point what? What would be our estimated unit? Sure, 8, 9. It's an estimate, right? So you want it to be close as you can get it. So we'd say maybe 15.8. And then what would our units be? Centimeters. And like I said, this unit is certain. Oop. However, this unit over here, we want to estimate. So we want to estimate 1 unit past what we're certain about, right? Does that make sense? It's really important that you do this in a lab setting, because what happens is this will impact any of your calculations afterwards. If you don't have enough digits in there, it'll actually change your calculation. All right, what I want you guys to do is to try doing this with the remaining problems, and try to do it as a team with your partner and make sure that your answers are pretty close. It's okay if that last digit on the far right-hand side is a little bit different, but the first one should all match. So I'll give you guys some time to work on this. All right, let's get together as a class and take a look at these, just because we're starting to run out of time. All right, so if we look at number 2, we've got little hash marks in between 15 and 16 now. So we are certain that it's definitely going to fall within what range? Yeah, between 8 and 9, right? So it's got to be 15.8. And then we want to estimate our next digit. What did you guys pick? 5. So 15.85. That sounds good enough to me. And then our units would be centimeters, right? So we wanted to estimate 1 digit past what we were certain. All right, number 3. If we look at it, it definitely is between what? Looks like it's definitely between 15.3 and 15.4. We've got hash marks in there for the tenths place. So it's got to be 15.3 something. We want to estimate 1 digit past the tenths place. What do you guys say? 2? Okay, so 15.32 centimeters. Sounds good to me. The main thing to remember is we want to estimate this last digit. It's always going to be estimated. All right, what about number 4? It looks like it's on 15.5, almost exactly. However, we still need to estimate that last digit. So 1 digit past, so maybe 15.50. It's fine to have 0 as your last digit. Still fine, just estimate that last digit always. All right, what about number 5? It looks like it's right at 16, right? At least to me it does. So I'd say it's definitely at 16. Do I just do 16.0? 0, 0, right? Because we've got hash marks already for the tenths place, so we need 1 additional unit. So it should be 16.00 centimeters. Again, we want to estimate 1 digit past the units that are shown. All right, what about number 6? Looks like we've got 12.3 something, and then we want to estimate the last digit, maybe 5 or 2 or something like that. So I'll just estimate it as 12.32 centimeters. Again, we've got the tenths place shown in the hash mark, so we want to go 1 past that to the hundredths place. All right, number 7. Looks like we've got tenths place shown. So it's definitely after 9.3. And then it's pretty dang close to 9.4, so I'll say 9.39 centimeters. Does that make sense? All right, and then the last few, let's do 8. It looks like we've got ones places for the hash mark. So for the one over here, what would that be? It's definitely past 21, so we'll say 21. Then we want to estimate maybe 21.9 Celsius, right? So we only want to estimate to the tenths place. We don't want to go past that, though. All right, what about the one over here? Looks like it's about 36, so we'd say 36.0. We still need to estimate that last digit. All right, last but not least, we've got these meniscus ones. Again, we want to measure the bottom of the meniscus. So what do you guys think for number 10? 4.28. And that would be milliliters. And again, the hash marks show the tenths place, so we want to estimate all the way to the hundredths place. And then the last one, what do you guys think? 30.0, right? So the ones places are shown as the hash marks. We want to estimate one further, and we'd say 30.0 milliliters, but we do want to estimate past the ones place all the way to the tenths place. So I know this is tricky. The problem of the day, the last one, I would recommend working with the group. Double check your answers. I'm perfectly okay with you guys working together on the problems of the day.